Okay, let's see where this leads. Today's presentation is supposed to be about pushing mixture of experts to the limit with extremely parameter efficient mixture of experts for instruction tuning. And that is a gigantic workflow, but the background for this paper is basically that a Cohere about a week ago published this paper on applying the mixture of experts paradigm to both low rank adapters and IA3. And you're probably going to be more familiar with LoRa rather than IA3, but like just take it that both of these are um, very parameter efficient ways to fine tune the model. And this paper is going to be going over methods to apply mixture of experts over those two things. They only test with the T5 encoder decoder model, but their architecture is not unique to encoders, so it should be very easily transferable to LMs. Um, yeah. So when we when we talk about applying mixture of experts, we go from low rank adapters, the mixture of LoRa, and we go from IA3, the mixture of vectors, so MoV. And in this paper in particular, they make use of a soft mixture of experts, which if you've seen the soft MoE paper before, or if you've been to the week one lecture on MoE, you might understand this as although we have um like n experts, although we have like n experts in the low rank adapter or in the IA3 adapters, um, we make use of all of the adapters in computation and we mix the results together based on what the router says. So it is soft mixing rather than sparse mixing. And for this paper, they make the bold claim that using a mixture of vectors or using a mixture of low rank adapters performs much, much better for fine tuning rather than traditional IA3 or traditional LoRa. And like, keep in mind that even though we are drastically increasing the number of parameters by applying a mixture of experts, we are still using a much smaller parameter count than the full model would imply. So like maximally, even with 15 LoRa experts, you only go to like 5%. So there are some things in the paper that I'm not going to cover today for a interest of lack of time. We are not going to be talking about how to adapt to decoder-only models, as I mentioned. We're not going to talk about the hyperparameters used in training because there's a lot of bullshit that you need to change like the batch size or the exact learning rate in order to make mixture of experts training work. And those are implementation details that are not too important to know to understand how MoE works with LoRa and IA3 conceptually. And I'm also going to overlook some interesting notes on expert specialization, where they look at the routing probabilities for each of the individual experts, and like they show that their experts, that some of their experts perform much much better on certain tasks than others, which is interesting, but is not what I'm going to cover. So oh my god, I should have disabled the animations for that. So let's talk about the basics for anyone who does not know what IA3 is or someone who does not know what LoRa is. So in LoRa, you have a normally like in any kind of linear layer, you have a weight matrix and you take an input vector and you multiply it by the weight matrix and like outcomes and output vector. Very simple. For LoRa, you have these two different matrices that are both like much, much smaller than the pre-trained weights. So D would usually be something in the orders of like, let's say 4,000 for Llama 7B, where, and of course, this will be like 4,000, this will be 4,000, but the R constant, which is the rank of the LoRa, will be much smaller, something like 4 or 8 or 16. So the size of these two matrices is much smaller than the original weight matrix. But because of how matrix multiplication math works, you get when D passes through here, when D passes through here, you get a output vector that is still the same size. So you can add them together. And like most people should be familiar with the general idea of LoRa. And maybe the math here is a bit helpful for people to understand if they um, just try and build things. But yeah, most people should know about this. For IA3, probably less people in the audience know about IA3 because it's there's not much of a reason to use IA3 over normal LoRa. Um, in IA3, you don't have any trainable weights at all. What you do have is trainable input vectors, and you and like all of these vectors are the same size as the hidden states that get passed around in the model, like the intermediate values that get passed around in the model. So like you have the query, you have the key values, or like you have the value in attention that get adjusted based on these learnable vectors, or the hidden state in the feed-forward layer, the llama MLP. And these learnable vectors get multiplied like element pairwise with each of the with whatever the hidden state that's being modified in the transformer model, whether it's the attention states or the feed-forward states or whatever. And so there's a very quick rundown of how IA3 works if you are not familiar with it. Although I don't think this one slide will be very helpful in helping to understand how IA3 works if you have never heard of it before. Um, you can also feel free to ask questions about it right now if this slide is like extremely confusing, because the the bulk of this Cohere paper focuses on transferring IA3 to the mixture of expert paradigm. And if you do not understand how IA3 works to begin with, then it will be a bit difficult for for to understand what they mean by mixture of vectors later on. Yeah, okay, I'm just going to assume. Yeah, and for the normal mixture of experts layer, if you did not watch the week 1 lecture on mixture of experts, the idea for a generalized mixture of experts layer is fairly simple. You just have like you take any arbitrary function like that can be represented as an individual expert. So like this is just one layer that can be anything. It can be an attention layer, it can be an MLP layer, it can be a linear layer, whatever. And like you have n duplicates of that layer, which functions individual experts, and you have a gating network that operates on the input vector x before that so that you can get a list of routing probabilities or routing scores for that input x for each individual expert. And so the input x is passed not just to a gating network, but also to each individual expert in the entire MoE layer. And then the outputs of these experts are scaled by the probabilities given by the gating network. And the reason why I want to show this slide again is to emphasize like that this general concept applies for both sparse MoE layers and soft MoE layers. So this diagram here, which is from the OpenAI article about MoE, shows two black color experts to emphasize that those are their sparsely activated experts in their implementation of sparse MoE. But if we have if all of the probabilities outputted by the gating network are positive values that are not zero, then instead of having two black activated experts, all of the experts are going to be black and activated. And then it will no longer be a sparse MoE, but just a normal mixture of experts. that is soft mixed into a final output value. So with the idea of IA3 and the idea of low rank adapters and the idea of mixture of experts covered individually, we are now going to go over how we can merge these ideas into mixture of LoRa's or mixture of IA3, which is also called mixture of vectors. Okay, maybe I should pause here for a moment. If someone needs additional questioning or Q&A or anything on MoE, on IA3, or on LoRa before we jump into like the actual innovation or idea or whatever you want to call it of this paper. I mean, if the answer is no, then like I'm just going to skip. I don't. Oh, okay. Yeah, no. Okay. If everyone understands IA3, if everyone understands LoRa, if everyone understands mixture of experts, then we can jump into what exactly mixture of vectors is. So the diagram for MOV over here looks a little bit complex, but the code for it is just four very simple lines. And we are going to go through over each of the lines to describe what the MOV layer does. So the MOV layer, which is an extension of the IA3 parameter efficient fine tuning technique, first takes the input, which is either going to be the key values or the value values or the V4 hidden states within a attention layer or within a V4 layer. Using those inputs, we pass them to a router, which does the usual matrix multiplication to softmax to gain a list of probabilities for how much each expert should be involved in the current input that's being given to a model. Then using the individual trained vectors, and like each individual vector being a trained expert, you take the router scores and you multiply them by all of the vectors so that you end up with one total summed up vector. And like this is the final IA3 vector that you get from taking all of the individual expert vectors and combining them together into a soft mixture, because you sum over all of the individual vectors multiplied by their weight score from the router, and then you just multiply the final vector by the input to get the result. Which, and like this very small line at the end, that is all that IA3 is. You just have a trained vector that is element wise multiplied with the input for a particular layer. And the only thing that mixture of vectors does differently is that you have multiple vectors that are merged together by a router that adjusts the weight of each individual vector based on a probability given by what the router decides each vector should be weight given based on the input. And if that was confusing, then you should probably complain even more, because yeah, because although I feel like I understood this explanation a lot, I am not sure whether other people in the audience understood it. That is the mixture of vectors explained. For mixture of LoRa, the paper cares about low rank adapters to less. Is my understanding that Cohere wanted to um, sell mixture of vectors as the best choice. So their paper does not provide any diagrammatic um, picture of like how mixture of LoRa is supposed to work. But conceptually, it's very much the same. You just have, instead of a single low rank adapter, you have n low rank adapters. And instead of just taking the input into the LoRa and getting an output, you put the input into a router. The router gives a list of scores for how much each LoRa adapter should influence the current input, and then you multiply the input by all of the adapters, and then you multiply those outputs by the weights given by the router, and then you have a final output. And like because we have no drawing from the Cohere paper, you can like conceptualize this as this very poor MS Paint drawing of you having two experts, the input goes to both, and then they get joined together and come out. Yeah, that's it. So if there are any questions about how the mixture of expert paradigm is being applied to both IA3 and LoRa, then please shout.
Yeah, I think one thing that's interesting to note here is that in the usual MoE setups, let's say if you go back to the formulas, it's usually you take a mixture of the outputs of the experts. But because both LoRa and IA3 are linear, what they actually do is they take a mixture of the IA3s or the LoRa's, and then after the mixture, they apply the inputs. Which
Yep.
is which is a nice obviously efficiency savings, but it also has this weird notion of like actually what it is doing is it's generating a set of specialized IA3 or LoRa weights for that token or for that. I think there's some experiments with it at the
Yes,
sentence level.
yeah,
Yeah.
yeah, yeah. In a sense, this is like you are dynamically generating a new low rank adapter or a new IA3 vector for that is specialized to the current input based on what the router says the final combination of all the experts should be, which is cool.
Yeah, and you can't do this for normal, well, other MOEs because usually the experts have some non-linearity in them.
Yeah,
But yeah.
that interesting aside. Um, Now that we have covered what the mixture of LoRa and mixture of vectors is in a conceptual framing, we can now go over the motivation for doing this at all. And like, of course, at the beginning, I showed this slide on like, oh, the IA3, the mixture of vectors and mixture of LoRa performs better than low rank adapters and IA3. But is that even true? We you see, I've quoted this chunk from the QLoRa paper that was written in May, where it is stated that QLoRa performs equivalently to a full half precision fine-tuned baseline across a large suite of benchmarks. And the claim of this Cohere paper is that that's obviously not true because low-end adapters are not working their on their task, on their model, on their dataset. So this is a big question. And the next big question is like, why are you even using mixture of experts if you're not making use of the sparsity that is typically involved in large mixture of experts models? Because in the case of low rank adapters, you you could introduce multiple low rank adapters of a small proportion of multiple low rank adapters of small rank, or you could just increase the rank of the adapter. So there's an unanswered question of like, why not just raise the rank? In and so I thought about multiple ways to try and compare the performance of the mixture of parameter efficient paradigm to just normal parameter efficient tuning. And if you compare MoV versus I3, this was the most obviously beneficial technique because unlike low rank adapters for I3, the size of the parameters that you tune for I3 is fixed. You can't make the proportional parameters that you tune larger without changing the model itself. So the fact that you can go from here to here is inherently beneficial. So that one is obviously a point in favor of Cohere. Um, when we compare mixture of LoRa versus LoRa, it is clear that the rank 4 LoRa that they use over here performs worse than the mixture of 10 rank 4 experts over here. But it is not very clear, as I was mentioning earlier, whether a rank N LoRa, like let's say a rank 64 LoRa, is any worse than a rank 4 LoRa multiplied by 16 times, let's say. Another thing, another way that you could compare is by checking like, is a mixture of LoRa's better than a mixture of I3s? And the paper handles this question well. They do a series of appellations on different model sizes, and they generally come to a conclusion that um, for their task, a mixture of LoRa is more important when their model size is smaller. And the last way to compare, which I feel is the most important thing that we all should be comparing, is the mixture of vectors versus LoRa. Because right now everybody uses LoRa, nobody uses IA3, much less mixture of IA3. So if this MoV is better, then maybe we should all be moving to it. And what the paper claims is that MoV is much better for the same parameter budget versus low rank adapters. This is very different from what the QLoRa paper says in May, where they say that the rank of a low rank QLoRa adapter should match full fine tuning, which is this dotted line baseline here, and it should probably not be this low. So what is going on? Why are they different? Um, so I spent about an hour or so to do a comparison between the results and the experiment design that was involved in the Cohere paper versus the QLoRa paper. And like, there are a lot of differences. The MoV paper that we're looking at now tested the T5 series of models. QLoRa did Roboter, T5, OPT, Llama, Bloom, Pythia, a lot of models. Cohere used this one public pool of prompts task, which is, if I'm not wrong, it's somewhere in the ballpark of 100 million tokens to 1 billion tokens. QLoRa used Glue, Supernatural Instructions, Flan V2, Alpaca, Open System, Anthropics dataset, Longform, Chip2, probably more datasets than I missed. The evals used between these two papers, Cohere uses a Cohere follows the T0 paper in terms of the evals that they try to use. So they use a D series of evals that I've listed here, and that you can also see in like this previous table here. Like they have all of these evals. And QLoRa also has a lot of evals, and not just traditional evals in the numeric form, but also a lot of handwritten, like explicit analyses of individual examples that come out from the model, and it's not very apparently easy for me how I should be describing them. And finally, QLoRa tested a series of different ranks from 8 to 16 to 32 to 64. The mixture of LoRa, as used in this paper, used rank 4 and did not report any other results. And there might even be framework differences between the two papers, because this paper from Cohere was implemented with TPUs on T5X. QLoRa paper was implemented with GPUs on QLoRa.py. So I do not know whether you should be trusting the results as published in this paper, which, again, remember, they are claiming that low rank adapters perform much worse than full fine tuning, and mixture of vectors performs comparably with full fine tuning. And QLoRa claims that they perform as good as full fine tuning. So somewhere between all of these differences in all of the models and datasets and evals and ranks and hyperparameters and everything is the answer to why this difference in results exists. But I have no idea which one of these is the problem. So, we have this new point that I'm adding to the list of things that we're covering today, which is there's this huge conflict in reported values with other literature that I do not know how to resolve. And if there are ideas on what could be the most likely cause of like the discrepancy in the results, then I would be very delighted to like hear some discussion or ideas or I don't know, experiment design on like how this question could be resolved based on the reported results in the Cohere paper. I feel like it would be nice if we could start trying to use mixture vectors, but given this huge discrepancy, like I just do not know how much to trust the outcome.
Well,
Cohere,
what
yeah.
Sorry, go ahead.
No, go, like I was just about to respond to Fluffy, but you can.
Yeah, what I was going to say is that it seems like they first didn't do an exhaustive exploration of the LoRa adapter configurations because, like, at least from my experiments, configs are like the hyperparameter configurations are like the performance is very sensitive to even like slight changes. And there is like a Goldilocks zone that you can achieve. I don't think that they necessarily hit that, and using like rank 4 is very low. Like I don't think that's even a fair comparison. Um, so I don't like. I would take it with a grain of salt. Like I would actually like agree with your initial claim that they're trying to basically make the MoV look better than MoLoRa's, but in reality, I don't think they've done an exhaustive exploration of the
It
full
does seem like
potential.
like those are completely fair points, and like I also generally agree with the take and think that the results are a bit sus. But to be a bit constructive, um, I would probably like to ask you and like I guess the MOE lower community in general, what series of hyperparameters or like ablations, like what kind of experiment design would you have defined to make the results look more clear to you?
Well, a wider net around rank, uh,
Mhm.
LoRa alpha, learning rate, weight decay, and dropout.
I mean, okay, like
That's
they like you like okay. it is
I,
possible
I
for an
understand it
organization
isn't
with
all. Yeah,
infinite
I
GPUs
know.
to test all of them, but like,
Yeah, I
but
understand. Like higher rank probably would be a no brainer, right?
yeah,
And I would like
like what would be
I'm
the
a little
minimum
surprised
set
that they
of
didn't. Like,
hyperparameter to make you feel like this has large
that's the thing.
potential?
It's also dependent on the data set. Like at least
Mhm.
like in part the data set plays a role there. Look, like at the minimum, they should have at least compared it to the like proven out high performance configs for like LoRa's, right? Like it's just that they picked the like the minimum threshold, or even worse than the minimum threshold, which is not like it's not a fair comparison at all.
Yep,
I
completely
think the
agree.
easiest setup would be to use the QLoRa defaults, which I think already has rank either 16 or
Yeah,
something.
exactly,
Oh, rank 8, I
exactly.
guess. Yeah, 4 is
It's
way too
ranked
low.
64 on their defaults, and even Tim Detmer says like 64 is the most performant.
Yeah,
Yep.
so on this note, I also am running. So I think that the case where, let's say, the lower results are most likely to perform worse compared to full fine tuning is exactly in this sort of like multitask fine tuning setup. Um, I am also running some experiments on this just based on some other work, and I can run a baseline that's based on like full fine tuning skill aura, and we can have a set of results with a fixed set of models and using reasonable parameters and check. At least we have one data point that's directly comparable.
That would be wonderful, and it would be great if you could. Um, I guess I don't know, post it somewhere else so that so that it's not just the people in this lecture that know that that's going on, but like, yeah, posting about it in the Emily Laura Discord might be good, I guess. Um, Question from Fluffy: does Cohere apply LoRa to all of the linear layers? My understanding is yes. Right. I see. Okay. 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 So moving on to God, I need more water. Moving on to the last big chunk of this paper, which is the the topics that Cohere actually did do fairly decent ablations on, I would say. Um, they had a series of questions in relation to the design of the experiment. So they were wondering, how much is the performance affected when you scale up the number of experts? Um, Whether the routing strategy should be a sparse strategy, like top K selection, as is done in most normal MoE papers, or whether you should be doing the soft mixing as they end up mainlining in their paper, um, and whether certain inductive biases are important or not important in helping out for their mixture of experts routing. So, really need water. For the first question, they don't really show a very good pattern between 30 and 10 and 60 experts. They try and say that there's a slightly positive trend over here and over here, but like to me the graph between 10 and 30 and 60 is basically random. But but we can clearly see that the performance increases like from 10 to 1. So that is the extent to which they answered that question. For the routing strategy, which is probably the most interesting thing to me, they tried to compare top K selection versus sparse mixing, and generally they find that top K sparse mixture of experts performs worse than soft mixing all of the experts together, which is like exactly in line with what you would expect because more computational power is almost always going to win over a sparse approach. But what they also do find is that if you have n experts and you top K select k of them, it will perform better than only having k experts to soft mix together, which this is the soft mixing of 2, and this is the k selection of 2 experts over 10. So if for some reason you want to reduce the computational budget of your adapters, but you also don't care about the compute that you put in to the main weights of the model, which are going to be way, way bigger, you can use top K selection, but it's not really that useful. And the last thing that it does is this very weird statement about announced task information. What they really mean is like if they use sentence embeddings in their router rather than tokens, does it perform better? And they basically find that the answer is once you scale up, the answer is no. Inductive biases out. And so, in summary, Cohere released a paper about mixture of vectors and mixture of flora. The results are positive, but are a little bit sus in light of other papers like QLoRa. They convert the IA3 method and the no-rank adapter method over T5 to use mixture of experts. And they generally advocate for using a soft mixture of experts rather than a sparse mixture of experts because sparse performs worse in this situation. And that's basically it. Chris. Okay, so just reading both of the chat channels right now. There is a gulf between T5 TPU and Llama HF GPU. Absolutely, it is horrible. Probably the implementations are somehow different despite being the exact same model.
Yeah, but even like who uses like T5 right now?
Well, you should tell that to the Open MoE project because like they're working off the T5 stack, right? Like despite the fact that they're training a decoder only model, they're working off of it in order to use the mixture of experts code over there. Like everyone at Google is persistently, eternally in love with encoder decoder models to this very day, and that is why they publish stuff like soft MoE or expert choice routing, where the ideas conceptually work really, really well with encoder decoder models, but are kind of hard to imagine working out with decoder only models. And it's not that MOV is better per se. I I am not sure if I would. I'm not sure I would make the case that MOV is going to outperform MO LoRa in general task and at all scales, even if that's what they report. Would it work if you remove the softmax in the router and multiply by the logits? Yeah, I guess it would. The difference is like the difference is just the irrelevant routers get scaled with a larger factor, and the relevant routers get scaled by a smaller factor, and there's a general increase constant, I guess. But I don't see why you would do it.
I feel like if you did that, it would be, I guess, mathematically cleaner and like, um, yeah.
Okay, so it's mathematically pure somehow.
Yeah, because like with LoRa, it's like a low rank layer. With this,
Yeah.
I think you can write it as a tensor network or something. Like if that's the reason why it works, yeah, and you could potentially extend that.
You will have to sketch this out for me because I'm mathematically illiterate. I just learned what an eigenvector is today.
I don't even know if like it would work, so someone had to make that
Okay.
experiment first.
Yeah, but it would just be, have a softmax or don't have a softmax. That's it.
Yeah, sometimes having a random nonlinearity helps, but yeah, with the especially in Molora, you can actually simplify the math if you merge in the routing weights into I think the first low rank weights.
How does the simplified math work?
Oh, because you just have like two linear matrices instead of having a softmax. Yeah, you just yeah. Does that make sense? You have
Yes, maybe, no.
routing weight matrix, right, to determine how much you're weighting each LoRa. That's just a linear
Right.
function, and then you have your LoRanks, so you can combine those.
Ah,
The
okay.
first one, yeah, I think, and that gives you small number of parameters total.
Right.
But you give up the nonlinearity, which I would not be surprised if it slightly
It's
improves
magically
performance.
responsible. Oh, the code is public. I did not. Oh, it is not. God damn it.
Not scammed.
Yeah. Yeah, okay. Does anyone in the audience have a desire at all to present a paper next week? Because I am persistently stuffed for time. I rushed this entire presentation today in the afternoon, and I do not think I can replicate that next week.
Yeah, I'm not. I'm not. I don't have the time to do it, but I would recommend the. I think the IBM, was it the MO, the new
Oh yeah, that one. Ah,
mixture.
it, yeah. Like insofar as I want somebody, and that somebody can be me. Insofar as I want somebody to do a takedown of that paper at some point because it seems very sus to me. Yeah, I agree with that paper as a good recommendation choice. Um, my my guess is that it will be a net negative direction of research in general because number one, they're IBM, and number two, because the whole paper just describes so much, so many things that exist as prior literature in the general MoE paradigm as these new innovations, which
Yeah,
is
it's like it seems like we're seeing more and more of ads disguised as papers. I'm not
yeah.
sure, like uh, something unique that is happening now, or is it just because of the frequency?
And when we blame them, there's too many papers. There's just so many papers in the world right now. You have to. you kind of almost have to indulge in the dark arts of advertising in order to get enough attention.
Yeah, but then you increase expectations so much that
Yeah,
you
like
know
everyone's always disappointed. Like, you
most
know,
papers are overrated, and then like actually the ones that don't advertise, like I find those more enjoyable and also more innovative sometimes.
yeah, from an epistemic perspective, they're definitely way cleaner when they don't over advertise. And
Also, like the IA3 explanation, at least for the MOV, it seems like also like they kind of overcomplicated it. It's a pretty simple architecture, and like you said, it's pretty transferable across different MOE arcs.
yep, I mean, I do feel that their provided 4-line code snippet was really helpful in understanding
Yeah.
because it is really simple to dissect. Okay, so we do have a projected paper for next week, which is the IBM paper. Okay, not next week. We have a suggested paper, which we can do the next presentation, which may not be next week due to a lack of presenters or a lack of manpower. But the suggested paper next week is the IBM paper.
Sign me up to do it. Like, sign me up to do it for next week, or I'll do it next week.
Okay, splendid. We have a great volunteer known as Artem, who may be able to give a presentation, who I will say is allowed to back out if he does not want to do it. But okay, next week IBM paper. I will post the link to that in the Mixture of Experts reading group thread if Artem does not do it. And with that, we can end the presentation, I guess. That's it. End.
Thanks for presenting.
Yeah, no problem.
Yeah, thanks.